Colin, you want to grab the camera? Okay, there we go. All right, so I don't have to stand in the box anymore. Okay. All right, so I am going to go through this section, well, not just because we're behind, but because we're not really, but I want to talk about nilpotent solvable groups. These are kind of special types of groups, and they're going to come up a little bit and then after this, we're going to talk about series, misnomer series, I think. But anyway, I'm going to talk about series a little bit because that is one of the applications for simple groups. This is why, you know, we did all these problems with the zero theorems about, oh, can there be a simple group of order 56 or 112 or whatever? Why do we care about that? When we get to series, we'll see why simple groups are kind of important, because in a certain sense, they're sort of building blocks of all groups. So first, we're going to talk about nilpotent. So now, notice that the center of G, which I'm going to, I'm inductively going to call this. So what I'm going to do is I'm going to build up these groups that are subgroups of G that are generalizations of the center of G. Now, of course, the center of G itself, set of everything in G that commutes to everything, is a normal subgroup of G. We've seen that. Now, consider a function that goes from G into so consider this canonical homomorphism where every element of G goes to the coset GZG, and let let C2G be the inverse image of this of the center of this, right? So what we're doing is, of course, we're looking G mod ZG is a new group, right? This group has a center, right? Maybe it's only the identity, and Z2G. So that is to say, Z2G is the set of G and G, such that if I call this pi, now notice that the center of this group is a normal subgroup of this group, and so its pre-image is normal. So that is to say, now you might guess what we might do here. So in general, okay, inverse image of center of G mod GJ on 20. Under the projection from G in this, right? Because remember, inductively, each one of these Z sub JGs is normal. And so this makes sense, and you just keep pulling back the center. So what this gives rise to is this gives rise to a sequence. The identity contains C1G. Of course, this is the center of the original group G inside C2G. So this gives an increasing sequence of groups. Notice that each of these groups is normal in G, right?
Increasing?
What? Yes. Right, because if you look at this first map here, the center of this first map, when you're trying to define Z2, contains at least the identity of this thing. So the pre-image contains at least the center. So Z2 contains the center. Notice that if you have anything in Z2, it goes into the center, and anything in the center, here goes to the identity. Right, and so it's in the center. So yes, it's increasing. We say that is to say, when you do this crawling up here, notice these are all subgroups of G. If you can actually reach the top, if you can reach G in a finite number of steps, then we say that G is a nilpotent. Note any abelian So one might consider nilpotent to be a generalization of abelian. And actually, I'm going to give you a theorem that sort of shows this in a way. Let me tell you what happens in the abelian case. In the abelian case, you go E. This is the center of G. If it's abelian, the center of G equals G, and you actually reach G in the first step, right? Here's another theorem. Finite. Does anybody see why that's true? Why is it true that a P group has to be nilpotent?
Non-trivial.
Okay, that's exactly right. Okay, so consider the pre-image. The okay, so let me point out first that this thing right here is also a P group, correct? Because In fact, the order of that group must be a divisor of the order of G. G's a P group, so this is a P group as well. So the center of this thing strictly contains the identity which is the coset Cj minus 1. So it strictly contains the identity coset, right? So strictly contains so the sequence So the sequence of these groups, these subgroups of G must be strictly increasing. Right? Since G is finite, which is an assumption, I hope I wrote down, I did. It's finite. Okay.
For that line on the top of that section there, the ZJ strictly contains the ZJ minus 1. I think I'm missing something, just like how you got that strict.
Well, because what happens is, for example, there exists a coset X Cj minus 1G in the center of G mod Cj minus 1G. You agree with that, where X is C minus 1G. So there's a non-trivial element of the center, right? Assuming that this wasn't the identity of the group.
Okay.
Right? Whatever that X is actually here, right? Because remember what this is so X is in the pre-image of this map, right? Because X goes to this coset here, right? And Cj plus 1 is defined as pre-image, right? Since X actually goes to the coset X, which is in the center, that means X is in the pre-image. But X is not in Cj minus 1G, and so you get something new. And so that's why it's strict. Because X lives here, but not. That makes sense. Okay. Here's another theorem. Okay, so what do we have so far? We have that anything that's abelian is nilpotent. We have P groups for nilpotent. This one actually helps us stick some stuff together in the following sense. The direct product of finitely many nilpotent groups is nilpotent. So my proof here is really going to be more sketch. There might be some details we can look at. So I'll make some assertions along the way here. By induction, you need only prove this, that H and K are nilpotent, and so is H cross. Because if this theorem is true for two, the rest of the induction is pretty easy, because if you assume it's true for n, right, then if you look at n plus one groups, the group the first n there, by induction, that's nilpotent. And now you're back to the two case, right? Everybody okay with that? Okay, so this is really what we want to sort of outline here. So why is it true that if H and K are nilpotent, so is H cross K? So let's look at this sequence of maps inductively. Assume that CNG let me point out here that, of course, this is certainly true in any one, right? Because what the statement says, the center of G is the center of H, that's the center of K, and that's easy to verify. Right? Now let's assume that this holds for some n, and we want to show that it will hold for the next case. And so let's consider the epimorphism. C and G my CNG. And I'm going to sort of dissect this thing. I'm going to take it apart a little bit. You can consider this the following composition. So let's break this into pieces here. G is defined to be H plus K, or H cross K. This goes by something I'll call pi into H mod CNH plus K mod CN K. And then I'm going to go pitchfork. H cross K, CN, H cross K, equal by definition. Well, by definition and by induction. And let me sort of break this apart here. By this notation, what I mean is pi H takes H, coset H, CNH, and pi K, this coset K, K, CNK. So what pi does is it reads the H coordinate and K coordinate, because that's what that is, and it spits this out. And I am going to find phi So this is an equality here, this is the way it's defined. This last one is an equality and this is by induction. And phi is this total composition, starting from here, remembering everything's h cross k, applying both pi and the pitchfork, and then and then identifying. So we'll call that that. So if you look at Zn plus 1g, this is equal to phi inverse of this. So it's phi inverse of the center of or the center of G mod Z and G, which is the definition, which is so take pre-image, pitchfork inverse, then pi inverse of this. And let's further dissect that as pi inverse that. Which is right, pi inverse. Right, bring it up here. So now what I'm going to do is I'm going to bring my pre-image up because if I want to find the inverse, I want to find the pre-image of this. Think of this as, think of pi as what it is. That is, it's these two pieces that operate on the separate factors. This is pi sub h inverse. K inverse. Z. And by definition, this is Zn plus 1 of H. And that's exactly what we want to show. So the ladder works, and this does what we need to do. So this is a biggie. If you have the direct product of 5 many nilpotent groups, it's still nilpotent. So here is a theorem that is very useful here. So this kind of, I like this theorem because it completely answers sort of your questions here. So here. This theorem gives a characterization of what nilpotent groups are if G is fine. Nilpotent. If and only if G is the direct product of zero. I like the way this kind of ties together, kind of ties the room together. Nilpotent groups mean it's the direct product of the COP subgroups. Okay, one direction of this is easy. Earth. What do we know? Each CLO P subgroup is nilpotent. Right? That's that was theorem 442, because each CLO P subgroup is a P group, so in particular it's nilpotent. For the other direction, let me finish my thought. Previous theorem. Because CLOP subgroups are nilpotent, and if it's a direct product of those, it has to be nilpotent. The other direction will require a lemma, but I skipped over actually in my excitement. So if H is a subgroup of G and G is nilpotent, oh, of course. Let me explain my notation here. If H is a subgroup, this notation is important in this theorem. I mean, is a proper subgroup of G, so it can't be the whole thing. You can put and see what happens if it is true. If H is a proper subgroup of G and G happens to be nilpotent, then H is a proper subgroup of its normalizer. That is, the largest subgroup of G in which H is normal is actually strictly bigger than H, right? Might even be all of G, but it has to be bigger than H. Let's prove this. I haven't defined this yet, but let Z0G be the identity. This is just a kind of a notational marker, just for convenience. And in the largest integer, such that Z and G is contained in H. Okay, so let me make a couple of remarks around this. Certainly, there is some integer such that Z and G is contained in H, namely n equals 0, right? Because the identity is certainly contained in H. So I know at some point, this animal is inside H, at some point. Let n be the largest integer. How do I know that this exists? Because G is nilpotent. So when I look at Z0G, Z1G, Z2G, it's all growing, getting bigger, bigger. And it eventually reaches G. Since H is strictly contained in G, there's some point where Z and G actually is not contained in H. So there must be a large integer where it still is. Everybody okay with that? Now let A be in Z and G minus H. but not H. Such a thing exists by our previous statement. So for all H, AH, the coset, equals HA, ZN. That's because A is in the preimage of this. So when I look at the coset AH, the coset, by this definition here, this coset, this is in the preimage at the center of the previous. The coset AZN is in the center. And so AZN commutes with this for sure. So what does that mean if you kind of take apart this coset here? So AH is equal to AH equals H prime, where H prime, right? Because this thing actually lives over here, so it should be AH times some H prime. And so this means that this conjugate so A inverse H. And so A is in the normalizer G of H. But A is not an H by construction there. And so this establishes theory. So in other words, that is normalizer G of H strictly contains okay. Any questions on that? Let me before we discuss the other direction to prove 445, which I'm a big fan of, let me introduce this. Here's a corollary before we get to the proof theorem here. If G is finite, nilpotent. Of order n, and n divided in G has a subgroup. This is a cool theorem because previously we know that, for example, we've had homework problems like, for example, that S5 doesn't have a subgroup of order 30 to 40, right? So immediately now that you know that I've written this corollary down, you know that S5 can't possibly be a nilpotent group, right? Because it's got divisors of its order. So what is it about this? Does anybody know why this is true? What is it about nilpotent groups? Let me kind of draw you a diagram of the corollary. So G, if it's it's nilpotent and finite, is the direct product of its CeeLo P subgroups. Do I agree with that? And so the order of G is little p1 to the A1 at the little pk to the AK, where PIAI is the order of the CeeLo P group, right? Suppose, I'll call this M, suppose M divides N, then M equals P1 D1 by PK DK, with each DI less than AI greater than or equal to 0. If I agree? So how do I construct a subgroup of this order? Right, this is part of what we know before part of the CeeLo theorems. Notice this P1 by itself has a subgroup of order PI to the BI for any BI less than or equal to AI by the CeeLo theorems, right? So pick a subgroup of order PI, BI, P2, B2, and so forth and so on. Pick those subgroups, take their direct product, and that's the subgroup you want. In fact, there's probably many of that size. Okay, any questions? Okay, we'll look at the proof again next time and finish up the stuff. Yeah, how about you all out there? Any questions? Everybody okay? All right. Well, y'all have a good one, and we'll catch you next time.
Thank you.